Again, welcome to basically election day class. I hope that you guys have voted. And if not, I'm going to try to make this one as fast as I can so that we can finish the circuits for two things, so that you can go and vote, and also so that you can go and watch the election basically results. And happy new 4 years basically from now on, whoever is going to be elected and whoever is going to be a representative. The main thing is to do our duties, okay? Now, today's topic is about electrical circuits. So I'm going to remove this background just to remind you guys to vote, okay? Because I want to demo the circuit for you guys at some point, okay? Where is my none? Okay. And so let me first of all share with you the screen where we are right now. So again, today's topic is on all about the circuits, okay? So electric current, we'll try to understand it. And basically that's the flow of charges. Historically, because of some basically conventions, we were talking about it, and when we were developing currents and so on and so forth, we came up with the convention that electrons are negative charges and protons, or the nucleus of the atoms, are positive. It turns out, and we didn't know that then, that the electrons are the ones who are responsible for currents and for almost everything that has to do with the day-to-day interactions. So the flow of the current actually is in the opposite direction with which the charges are moving, and that is because of the negative sign. Of course, you don't care, and nobody cares about it. So if you put an ammeter, for example, and you connect it in your circuit, you will see this is the ground, and this is basically where you connect the red to. I cannot see it from here. The two red ones is where you connect basically where the positive from the battery is. So you see that this one will move to the positive side, and you can say that the current is moving this way. You and I know that the electrons are moving in the other direction though, but just that's a small minor detail. So this is an ammeter. This something will tell me how much is the current is flowing. This specific ammeter measures the current in two scales actually, from 0.2 all the way to, from negative 0.2 in the opposite direction all the way to 0.6. That's on one scale, that's this scale. And then it measures it also from -1 all the way to +3 amps. So this one cannot be used for tremendous currents. 3 amps, by the way, is tremendous current. Okay, it's a lot of current, because that's 3 coulombs that pass per second. That's a lot of current, okay? Voltages is really what drives the current through. This is also a voltmeter. The first one was called an ammeter. This one is actually a voltmeter. The same thing, you connect the ground to the black one, and you connect the positive to the other side, to one of the red ones, depending on which scale you want to read, to the top or the bottom. So this is a quick introduction to basically the devices that we use in electricity to measure currents. I have actually another device in here, which is even better than that. And this one can measure for me voltages, can measure for me resistances in ohms, can measure for me frequencies, capacitors. So there's measure a lot of things. That's why this one is called, it can measure currents also, both in the AC and DC format, in small values or higher values. Again, you always have the ground in the black one. For the voltage and anything else, you use it on this side. For the currents, only you use it on this side, depending on the value of the current, if it's too strong or too weak. This is a multimeter, okay? Actually, I love it, because it saves my day a lot, because I can't read, for example, the values of the resistors in terms of colors. They're just connected in here, and I can find out exactly what value I have in that resistor and change it and put another one. So this is some of the things that we use to detect currents, okay? And they are mainly voltages and currents, okay? Those are the two quantities, the main quantities that we deal with. And then I mentioned the resistance. Let me grab another one, because this one is connected already. This is a resistor. I mean, you can see it because it's trying to focus on me. The camera is trying to focus on me, so hopefully it's going to focus instead on it. Okay, so this is a resistor, and you can see color-coded. Okay, if you have a magnifying glass, you can see exactly what colors are, and you can read the value based on the color. Okay, otherwise connected to that multimeter, it's going to give you the value. That's another quick and dirty way of actually getting the values. Okay. We're going to learn about, and they're essential components. I mean, all of this electrical things that you have in your house or your computer or your phone or calculator or anything else, they usually have resistors in them, and that is a fact of life. The wire itself, and any wire you have, has a built-in, is actually a resistor, okay? Albeit it's a small resistance, but it has a resistance nonetheless, okay? So that is a fact of life in terms of electrical components. There are other components than resistors. For example, I have a diode in here. Okay, that is a diode. You can see it has two legs sitting on them. Okay, and you have transistors. Those are nonlinear circuits. You have condenser capacitors. You have inductors. Okay, like this one. Okay, you have a bunch of stuff in here that you can use. This is another inductor in here, or this is actually that you can use to induce current currents through it. So you have a lot of these things in here, a lot of components, motors. Okay, this is a motor. For those sitting in physics 11, that's part of their project. Okay, lab project. So resistors is an important component because you will find it almost everywhere, no matter what circuit you do. You will have that. Okay. Then we're going to talk about Ohm's law, and Ohm's law, basically, in a nutshell, it connects both this one, the current, which usually the symbol for it is I, and the voltage, which is usually the symbol is V. And the Ohm's law says V is proportional to I, and the constant of proportionality is actually this R. So these three quantities in Ohm's law, they're connected through this relationship. V equals to Ri. Okay. We're going to distinguish between two currents, DC currents and an AC current. Okay. In your household, it's an AC current. That's what the power company delivers to your house. Okay. But in every situation, you are not going to use the DC current. That is not what your actual device uses. It uses a plug or internally another device. For example, my computer, I have the plug in the back in there. And your phone charger, for example, there is that part of it that goes into the wall, and that is actually brings down the current to convert it into a small voltage so that your phone can actually charge. You're not going to connect 220 directly with the wires to the phone. It's going to burn quickly. Okay. So, and that makes the current actually into a DC current. Okay. So what we use actually at home, I mean, what we actually use on our devices are DC currents. Okay. So we need ways of taking an AC current. That's the only way we can actually produce, or at least that's the easiest one we can produce. And we convert that into a DC current when it comes down to its consumption. Okay. Resistors, for example, they don't care. They can use actually the AC current fine. But most electronics, they don't. They have to really use DC currents. Now we're going to talk about the speed and source of electrons in the circuit. Basically, we try to have an understanding of what in the world is similar to what we did when basically we have to understand what the current is, how charges move inside a conductor. Okay, we'll have a theory basically to explain it. Then we're going to talk about power, and power actually connects these two quantities too, V and I. The power, mathematically, you can write it as the product of the voltage and the current. Okay, since I know the voltage in a resistor is given by this expression, in a resistor and a resistor only, the power is given by this expression. So this is an alternative version of it. You don't need to remember this is the one to remember. Okay, that's worth remembering. So if you go to the store and they ask you for, and you're buying, for example, 100-watt light bulb, that is how much power it has. And if you connect it to 120 volt, so how much current is going to run through it? It's given by 100 divided by 120, or 10 divided by 12, or 0.8? I don't know. Let me do it quickly in here. (0.8333) basically repeating. 0.8 amps. Okay, so that is what a 100-watt light bulb will run. Okay, that is the current that runs through it. If you're curious, for example, you want to know how much current runs through a 60-watt light bulb. That's another light bulb you can buy. It's again 120 volts for the same voltage, because that's what the power company will deliver to your household, times the current, and the current in here needs to be 0.5 amp. Okay. So which one is brighter? Of course, the one that has a higher current. Okay. The 100 watts is brighter than the 60 watts. 60 watts has less current in it than the one that is 100 watts. So this is some of the common information. As also a consumer, you really need to be aware of these things. So you really need to have an understanding, not just for the sake of Physics 10, but the sake also of consumer trying to be aware of what you need to buy for your household and things like that. So it's important. We're going to talk about compact fluorescent lamps, which are not as much in use, but the LEDs are, okay? LEDs are, and case in point is the diode I was showing you, okay? I'm going to yank it from here. Okay, so this is an example of that. Okay, but this is a different type of electronics that is not really the one that you're familiar with. It's not one that is probably, but it's basically, I don't know. Can I show you this quickly now? Okay, you see the legs in here? They are at 2 different lengths. Okay, all diodes have that. And that is because they can only be connected in one way. The current can only flow in one way. This is how they tell you which way the current can flow on this specific diode. Okay, that's the convention for it. They make one leg longer than the other, so that if you want it to light up, you have to connect it in that fashion. You cannot do it in any other way. Okay. So, and then finally, we're going to talk about the 2 kinds of main connections. There is the so-called parallel, which is how your house is connected. Okay, and there is also the series. That is how your Christmas lights are connected. Actually, the lights that one light bulb after the other running through that. But this is because everywhere you connect in your household, you have 120 volts. They are all connected in parallel. Okay. Sometimes you do the series, but it's not advised for some of the things because it can be problematic. So I mean, this is a bad analogy, honestly. It's the difference in pressure in here that generates the excess pressure for the fluid to move onto one side so that the 2 pressures are the same. There is actually a better example for the current, and that is a difference in height. Okay. So if you have, for example, let's say, for example, the ski lift example, okay? You are skiing as long as you are in the incline. If you are in here, you're not really skiing. You're just, because of the inertia, you keep on moving. But if you stand in here by yourself, you're not going to move. So if somebody stands in here, he's not going to move. If somebody stands in here, they're not going to move. If you stand in here with your skis on, you're going to come down the skis, okay? So this is a difference in height. As long as there is a difference in height, the ski can happen, basically, in a nutshell. As long as you're an incline, of course, otherwise you're going to fall, okay? If you are on a mountain, you can ski as long as there is an incline. If you are standing, you just get off of your car and you stand on near the hill, you're not going to go anywhere. You're going to stand in there forever and ever, okay? Now, if somehow you can manage to come back to a lift, okay, and you're taken up, the minute you are here, now you have a height. If again you are on the edge, if you stand right, if you're lifted to the edge, you're going to fall down. So in this case, as long as there is a difference in height, there is ski. Okay, and if it's connected this way. Same thing with the circuit. As long as there is a difference in voltage, there is a current. Okay, if this battery, there is another battery. I know I have another battery. If the battery, for example, the 2 ends, the positive and the negative, run into the same voltage, then you have a problem. Okay. This battery in here, the difference between this side and this side, or actually this side is higher than this one. So this is the top of the mountain, this is the lower of the mountain, and how high it is, this battery is 9 volts higher, okay? So if I connect a wire between these two ends, this is the same thing as the skier going downhill, okay, going from here to here, okay? Inside the battery, what happened in this case is the lift, is that example in here with the lift or the elevator, okay? The minute the charge lands on this side, which is the negative, you can see it in here on the side, which tells you that this is a negative end, okay, cathode. If it lands in here, the battery, since it has energy, will take it and put it back in here, okay, put it to the higher 9 volts. Now, if you're still connected, now the charges will fall to the lower voltage by 9 volt, the height in here, okay? So what matters really is the difference in voltage, the difference in height. It doesn't matter how much high this one is and that one is. As a matter of fact, if you're looking at your wall plug, the difference between the two ends, the two basically holes in the plug, is 120 volts, okay? That difference doesn't matter how much one of them is and the other one is. So instantaneously, one of them could be, for example, 5 volts. The other one is 120 plus 5, okay? The only bad thing about this example is the fact that because the current is actually alternating, they switch places, okay? Sometimes this one is higher, sometimes the other one is higher. Furthermore, it's actually not 120, it's 170. It's on average 120, okay? So that's what the power company tells you, we're going to deliver to you on average 120. So when they tell you it's 120, what they mean with it is actually the average value, okay? Because it flips back and forth, back and forth, back and forth, okay? It flips between 170 and negative 170, and that actually, there is a mathematical formula where that actually averages to exactly 120 volts, okay? So this is the example, back to the example for the like the example for the lift in here, for the elevator, is you have a pump in here. As long as the pump is working, the minute the next drop of water comes in on this side, and it wants to keep this height, okay, the difference in pressure. It wants to keep the difference in pressure between this level and this level. Let's say, for example, you need, I don't know, for example, 120 Pascal in difference, okay, between these two sides. If that's the maximum, that's the only, that this power can do that, the minute the next drop in here and this level, and the next rise in this level, that should be less than 120 now between this level and this level. So what it does, it takes this extra water and basically pushes through the pump and put it in here back, so that it brings back the difference in height to be 120 volt, 120 Pascal. This is the same thing as a battery that has 120 volts, okay? As long as the battery still has energy in it, and it does that, this is a functioning circuit. This is exactly how circuits work. They are similar in this sense. Same thing with this pump, as long as it has still energy in it, and it can pump the flow of fluid, so that to keep that difference in pressure to whatever that the value was, then we're in good shape, okay? So this is an analogy with the water flow, okay? So electrons are the charge carriers, and they are free to move in conductors. So in a conductor, basically what we have two kinds of materials. Basically, we have conductors, and we have insulators. And thank God we have insulators, otherwise this place will be electrified everywhere, okay? The air is an insulator. Charges do not move in air unless there is tremendous voltage difference between them. Then at that point they will be, they can break the air and move in it, and that is the lightning actually, okay? Lightning strike, that is what it is, okay? So air is an insulator, wood is, plastic also. That's why almost in every conductor, you have a material that is plastic in here to insulate it, to protect it. Otherwise, this whole wire will be exposed, and you cannot have, and you will have problems when you're connecting things. This is another wire that is also, they use a insulation in here for it, so that it conducts electricity. Now, conductors, on the other hand, the example that we use in daily life is copper. There is also gold, and also silver, and so on and so forth. Those are conductors. All metals actually are conductors, metals, okay? Some of them are better conductors than others. So what a conductor is a material that has a bunch of electrons basically free to float. The minute you put a battery between the ends, the charges will move, okay? The electrons will move, okay? The protons and the nuclei of the atoms, they cannot move. They are too anchored and they're connected. So the electrons in a conductor or a metal, they don't belong to a specific atom, they belong to the community of the atom. So the minute there is a voltage difference, they start moving, okay? Fluids also can be conductors if they have ions in them, okay? So again, which statement is true? Electric current is a flow of electric charges, okay? Electric current is stored in batteries. There is no current in a battery. What is stored in a battery is an energy, okay? It's a difference in potential. It's usually chemical energy, like this battery I was showing you earlier. That is actually a chemical energy, and I don't know where I put it here, okay? That is a chemical energy or other forms of energy. So that is what is stored. So it's not, of course, both A and B, and it's not neither A and B. The correct answer is this one. Now, here is note, and this is part of the question of the day, is electrons are responsible, only ones responsible, not anybody else, for electrical currents. So this is item 1 of the day, okay? Because we want to remember that. So the current now is measured in amps, and I already mentioned that. In the system of units that we use, okay, to measure the currents, to measure any units, we usually use the M, K, S, and A. M for meter, K for kilogram, S for second, and now we have this unit, the ampere. The picture is completed now. This is what we mean when we say the SI system, le Système International. So this is exactly what we mean by it, MKSA, okay? So the ampere is the unit of the current. So that is, by definition, basically one of the fundamental units, and from there you can define other units. Like the volt, for example, I was talking about all along, that is actually not a fundamental unit, but rather it's a derived unit. It's just like the Newton, okay? So the speed of the electrons, or the drift speed through a wire, is slow because of continuous bumping into the wire. So when charges flows through a circuit, voltage is established across a circuit. No. I think I'm going to jump to the last side of the picture to give you exactly an idea of how this thing is working, because it's probably not a good descriptor in here. So let me go into this in here and create a new page in here, or go straight to page this one. And I'm going to share that screen with you guys. Stop sharing the PowerPoint and let's go in here to understand how currents work in a conductor. So share. So I have in here a piece. Let me have the drawing picture. I have a piece in here of a conductor of a given cross-section area. Okay. And it has a bunch of charges. Of course, in a conductor, charges, anything in here is not stationary. Everything is moving. But the motion in here is random. This one could be going this way. This one could be going this way. This one could be going this way. So the motion under normal circumstances is random. On average, there is no motion. Okay, because if there is a net motion, on average, we will have a current. Okay. So we don't have really a current because on average, the motion is random. Voltage difference. There is no voltage difference. If there is no battery, there is no the motion of all of them. All of these charges is going every which way. Okay. Now, if I apply a voltage, now I have put a voltage now. Okay. This is a voltage high, V high, and this is a V low. These charges now start to move on average in this direction from high to low, from 120 to the 0, or from where the 9 volt is high to the low, just like my example earlier with the skier or the flow of water. Okay, they start to move this way. But the problem with them is there are the atoms in here. So these are the electrons in here, actually the positive charges. Okay, the electrons are actually moving in the opposite direction, but think of them as positive charges. They start to move, and when they do, for a little moment, because they are subject to electrostatic force, which is their charge times the electric field, because there is an electric field in this region. After a while, they will bump into the atom. So they will be accelerated first, falling, and then they will bump into an atom. When they bump into the atom, the collision will send them every which way in random fashion, just like before the applied field. Then they remember that they have to continue moving. Okay, after they come out of the collision in all possible directions, after that collision, they will start to accelerate again toward the lower high, to lower potential, and then they will collide again. So the time between each collisions is the time when they're actually moving, and that is what we call the drift velocity, because they will be drifting on average in one direction. Okay, and the average of the random collisions is just like this average, which is 0. So the drift in here with which they move is actually the current in here. Okay, the rate at which how many charges will pass, the number of charges that pass for every second on the other side is actually by definition what the current is. Okay. These random collisions in here will determine how good the conductor is. If the time between collision is very large, that means that you can speed a lot. But if the time is very narrow, that means that immediately after they accelerate, they slow down, they slow down, they slow down. So actually the time between collisions is a very, very important concept in here, trying to understand electricity. And that's what makes a difference between a good conductor and bad conductor. As a matter of fact, if the time of collisions is almost nothing, then in this case, there is no way. They're not going to go anywhere. So the minute they try to accelerate, they stop, and so on and so forth. So you really don't have a conductor. You have actually an insulator in this case. Superconductors, they use different technology altogether. I mean, that is actually it's a different process altogether. Okay, it doesn't involve collisions whatsoever. Okay. Semiconductors, on the other hand, they have a different technology also. They can conduct in one way and not in the other. So this picture, which is really a classical picture, the one I was showing you guys, is just to illustrate the point of the difference between a normal conductor like a metal, like copper that we use on a day-to-day basis, and also an insulator, for example, or a poor conductor like, for example, iron, which is some of you in Physics 11 are going to be using for your motors. Okay, so you will have an iron which has a very, very bad conductivity, relatively speaking, of course, compared to the copper. Copper is a much, much better conductor. I think it's like, what, 10 times better or 20 times higher than iron. So that's how copper is, okay? But just basically to illustrate the point, because the collision between the successive collisions for iron they happen more frequent than those for copper, okay? That's why copper is actually used in the industry. We could, I mean, there is actually better conductors than copper, namely silver and gold, but who wants to build his or her house out of silver and gold wiring, that is, okay? You must be super rich to do that, okay? And even if you do it, you risk that somebody else will come to your house, not to appreciate the electricity, but the wiring for the electricity, okay? It's going to be a very costly electrical circuit. So that is basically what this thing is talking about in here. Okay, the drift velocity and all of that thing. So the minute there is a voltage difference, then they start to move. They start to fall from high to low. For the AC, so this is the DC actually. The first one is the for the AC, the electrons, they move from one side to the other, so they are actually periodic motion, and it goes in a different circuits. So that's the in a nutshell what it is. So DC current, to go back, this is time. The voltage is more or less constant. Okay. In an AC current, so this is a DC current, direct current. In an AC current, the voltage actually changes periodically. And it goes from a high value to a negative high value. Okay? And it vanishes at some points in here. So on average, it's actually the current on average is 0 and the voltage on average is 0, but the power is the one that is actually more important. The effective current is not 0. So there's a difference between calling it average and calling it effective. So the effective current that you use at home, or the effective voltage that you use at home, is 120 volts. Okay, it's effectively as if it's a DC current running at 120 volts. So for that example, this would be the actual picture. Okay, it's much higher. And if this is 120, it maxes actually at 170. Okay. So any material having free charged particles that is easily flow through it, that is what that an electric field force acts on them. They are actually what is a conductor is. Okay. Electrical potential difference, the difference in potential between 2 points, and I already illustrated with the battery. Charges in a conductor flow from higher potential to lower potential. Okay. This ball, for example, is at a higher height, so if I drop it, it's going to fall at a lower height. That's similar to that. The only trouble with this picture, again, is the fact that the charges are electrons, so actually the electrons, they are falling from low to high, okay? I cannot do that, okay? But that's in actuality what the positive charges are doing, okay? They are falling from high to low. So we don't have negative masses in real life. If we have negative masses, all negative masses will fall to the ceiling, okay? Again, if the difference in height, if the difference in potential, if there is no difference in here, this ball is not going to fall. Okay. The minute I tilt my hand and I create a difference in height, this ball is going to fall. Okay. So that is the analogy with the gravity, and the analogy with the flow of water also same thing. High pressure and low pressure. When the pressures are the same, there is no flow. Okay. Here we have a battery. We have a switch. Usually we have a switch for protection. I cannot find my switches. I think they're in that bag there. I could have connected them. And basically we can run the current through it. Let me demo this thing for you guys. I have an LED in here. And the purpose of the LED is actually to show that there is a current. Again, it's going to light if the current is flowing in one direction. If I reverse it, it's not going to light. That is part of the process of how LEDs work. Okay, I need to bring my battery back into the picture. Okay, and right now I have a resistor of 220 or 210 ohms. Okay, so this is a resistor. Usually it's for safety, because I think this is only can support up to 5 volts. This is a 9 volt running through, how much current in here? I don't know. Let me see. Come on. 9 divided by 210. So that's 0.04. 0.04. And basically, most of the voltage drop now will be in here, okay? Because there is a 5 volt drop in across this guy. So the rest of the voltage drop is going to be across the other one. So I'm going to connect now my circuit, and if it's connected correctly, this thing will light, okay, as you can clearly see. So again, I'm going to remove it, put it on, so the circuit is connected. So what's going on? I have the positive in here, which is the red one, coming into the circuit. I'm picking it up with this green one, okay, from the positive, as you can clearly see. Let me unplug it right now, okay. From the green one to this line. Now from here, I'm picking up the positive of this diode, And then I'm picking it up in here again. It's dropping in here. So this whole thing is the same potential. That's why this connection is connected in here. So if you've ever played with a breadboard, this is the time for it, okay, where you can make your circuits, where you can have fun, you do whatever you want to. So I'm picking it up from here and I'm connecting it to this line. I don't know what this line number is. They're all numbered, by the way. And then it's connected to the resistor. From the resistor, the current is coming out, and it's coming through this negative side in here, which I'm connecting it to. This entire line has the same voltage where my second side of the battery is connected. So basically now I can connect it anywhere on this line and it's going to light. Just to illustrate the point that if I reverse, I'm going to change only this one in here. If I reverse the diode in here and put the long leg on the opposite side of the battery, this should kill any current in the circuit. Okay, and it's not lighting at all. But if I reverse it again, it's going to come back on. Okay, so this is basically a simple circuit that involves only two items in here, which is a resistor and a diode. Okay, an LED in this case. Okay, so this is another circuit in here. I don't have a light bulb, but if I do, it's the same thing in here, but it's simple enough that we can do that too. But I don't have a light bulb, so I use the LED instead. Again, these are some of the stuff that you see in circuits a lot, okay? So this is a switch. What is it? Switch? No, this is the switch. This is an AB switch. I think this looks like more of an inductor or something like that. Anyway, these are the resistors, okay? This is, I think, the condenser, capacitor, and whatever those things are. Anyway, so these are some of the elements in here. I myself recognize them from their symbols much easier than this one's in here and go and grab the right one in there because they have different conventions for them. And for the resistor, which is a main component for a lot of circuitry, you have these colors in here, and the colors, they have specific meaning, specific values actually. As I said before, you don't really need to remember these things as long as you can basically get a multimeter like the one I have, and then you're in business, okay? So the thing to remember about the resistance in general, it's inversely proportional to the cross section. Thin wires, more resistance. Directly proportional to the length. The longer it is, the wire, the longer it is, the more resistance. And of course, it depends on the material itself. So that's basically what the resistance is. There is a formula for it. The resistance is equal to the resistivity, which is a property of the material, times the length of the wire divided by the cross section. Okay. The old, basically filament-based light bulbs, the old ones, the one that basically use the resistor principle, they have this filament in here, which is usually made out of tungsten, that glows with the current in it. In other words, the resistance will consume a lot of power in this case to the point that its temperature reaches the point where it starts to glow. Okay. And that is basically how the conduction is in this case. And both sides in here is where the current comes in and comes out. Again, semiconductors like this example I was showing you earlier is actually a semi-example at work, because you saw that on one side it conducts electricity. When you flip it backward, it's not going to conduct electricity. So those are some of the semiconductors. They are always based on two materials from the periodic table, namely the germanium and also silicon. There are other compounds basically that use these ones in here. Okay. Superconductors, on the other hand, they reach zero resistance when temperature is super low. Okay. I think we have a little bit of time, so let's see here. Ohm's law, I already explained what Ohm's law is. It relates both the current and the voltage in the circuit. V equals to Ri. That's the mathematical expression for it. Again, for those sitting in physics 11, that was part of a lab that we did way back. Okay. Relationship between voltage, current, and resistance. So this is the relationship. States that the current in a circuit varies directly proportional to the potential difference or voltage and inversely. So this is basically what this says. V equals to I is equal to V over I, R. So this is the expression, the mathematical expression again, except that it's spelled in words. When you double the voltage in a simple circuit, you double the current. Because remember, the current is equal to the voltage divided by resistance. So if this goes twice, so instead of 120 volts, now you're dealing with 240 volts, then the current, whatever it was, is going to be doubled. So let's say, for example, we have a 10 ohm, okay? Then 120 divided by 10 ohms, it was 12 amps. Now 240 divided by 10 ohm is going to be 24 amps. So it's going to double also. So damaging effect of shock results from passing through the body, electrical potential difference from one part. So basically, why is this one is not electrocuted? Because there is no current running through him. So again, I explained the difference between the DC and the AC current. The AC is changing with time. This is usually a periodic function, and this one is a linear function. It doesn't change, okay? In the United States, the AC current runs at 120 volts. Okay, this is the effective voltage, okay? As I said time and time again, actually it varied between 170 and negative 170 volts, okay? Effectively as if it's 120 volts. So that is the voltage in the United States. It also has a frequency of 60 hertz. That means that it changes back and forth in 1 second 60 times. Think about it. The plug behind you or next to you on the wall, the polarity on it flips back and forth every second 60 times. Okay. The rest of the world in Europe and the rest of the world, actually, most of the rest of the world, except probably, I don't know, parts probably Canada, maybe, I don't know, Japan or somewhere else. They use 220 volts, okay? And they use actually 50 hertz. They don't use 60 hertz, okay? They don't use, the current there changes 50 times every second, not 60 times every second, unlike the United States, okay? Well, that's why if you're traveling abroad, you're leaving the United States, you really need to go and grab yourself usually they cost about $20 or something. They have all kinds of plugs. So you have to know where you're going. If you're going to Europe, they have those rounded ones and they're a little bit spaced. And in Britain, they have 3 ones and they have this weird structure. So you really have to know where you're going before you go, or get a big kit with everything in it, okay? So that your phone can still charge and can work and things like that. Okay, converting an AC to a DC, you need something like diodes, like the ones I was showing you. This is the picture that I had already showed you. And basically what they do in this case is, let me give you an example of a regulator. These are called regulators, okay? So you have a diode in here. The symbol for a diode in circuits is this way, okay? Let me try to think about it in here. And okay, I forgot the entire schematic in here. Okay, never mind, okay? I'm trying to think the current basically when it flows one way is going to come out from the other side. Okay, never mind, okay? So it runs through a regulator in such a way that only, because as you saw earlier, this one in here only conducts the current when it's in one direction. So if the current flips and becomes in the opposite direction, it's going to simply ignore it. The light won't go on, okay? So this negative one in here, the light will not show, okay? But you do them in such a way that they are actually happening not every half cycle, but not every cycle. You do it actually so that it happens only every cycle. And that is what I was saying effectively as if it's 120 volts, okay? Obviously, this is, there is another reason for it actually. Why is that too? And like I said, it involves a little bit of expression that involves averages in mathematics, but that's the reason for it. And again, for the same reason, okay? If you take the power, for example, the power is proportional to the current squared, and the current squared flips the sign from being positive, negative to just being positive. I already explained how this thing works. This motion is like the drunken man motion, basically. A drunken man, when walking out of basically completely drunk and wants to get home, usually he or she makes several steps forwards and one step backwards and several steps backwards, but on average, he's going to continue until he gets home somewhere, okay? So this is an analogy with it, and that's why we call it a drift motion, because it's not completely, he's not like a person who is not drunk where he goes straight out from wherever he's at to straight out, because there is collisions in here involved, okay? Yes, I hope that you guys have an understanding of what that means, okay? I don't mean to pick on anything in here. He has to be completely drunk for it to happen, so that he cannot stand basically on his both feet. So again, this is the same picture I was talking about in here, okay? So current is propagated through, no, that's not it. No, the electrons are actually, they bump into the atoms themselves, the nuclei themselves, okay? That's another misconception. The wall is not, so when you go, it's actually your computer has its own electrons already in it, okay? Again, electric power, I already gave the formula for it, and that's the same thing in here, as is expressed by this formula. Power is the current times voltage. The unit for the power is watts, and that's what you go and get from the power company. I mean, from the store to buy, for example, light bulbs. So you get them in watts. If you look at your back of your computer or next to the power supply in it, they will tell you exactly how many watts this one. I'm looking at this computer, this big computer that I used to run right now. I think I need to get rid of. I have to see how much power is in here. It says the current is 10 amps. No, wait a minute. This is not giving me the power. Okay, that's not good. Look at the back of your computer. Usually it's about 18 to 20 watts, okay? And yeah, that's 18 to 20 volts. Yeah, sometimes they give you the volts and the power and the current, and you multiply the two, and all of a sudden you have the volts. Otherwise, they give you straight out the watts, like light bulbs, for example, okay? Obviously, if you keep, for example, a 60-watt light bulb, and here, how is this one in here? The light bulbs in here. So, if you, for example, if you get a 100-watt light bulb, okay, what that means is this one will consume 100 joules for every second. That's what that means, okay? And remember the math that I already showed you, 100 watts, for example, when you plug it into the wall, that effectively is running 120 volts. This, you need a 0.833 amps current in it, okay, that's to run it. So you ask how much, basically, this one versus another one, for example, of 60 watts. 60 watts will run, again, 120 volts times, again, 0.5 in this case. It's going to work correctly in this case. So the fact that this is a brighter is because it's running at a higher current than the one that is lighter, okay? That the one that is running less current, so it's actually going to be less bright than the other one. So that is one issue. Now this one, they use a completely different technology, and they effectively deliver an equivalent power to a higher value in here, but running less current, okay? So they don't use resistors in this case, okay? They use this fluorescent lamps. That's basically how they use. So it's not this formula that you're going to rely on, okay? Let's see here. Again, another one, and you saw it in action, actually lighting up, is the LEDs, and this is what is used in screens. Actually, a lot of the screens, they use LEDs for their technology to light up, okay? So this is actually the new circuits, the new, basically, electronics use a lot of these ones instead of using these bulky ones that require a gas in here, or the resistors that overheat. These ones, they don't, and they light up exactly because of the way that I showed you the and the illustration. Okay. Circuits, as I said before, there are two main differences between them. Circuits, they can be in series, like the one I showed you earlier. That was actually a series connection. Let me show you again. Let me put the light bulb in here where it was. I mean the LED where it was. So the current leaves the battery and then is picked up from this side, of this wire, from the same node. Then it comes out from the other side. This is basically, there is a gap in here, okay? If you're familiar with the bread board, there is a gap in here between this side and this side. This entire side is joined. So the minute I put it in here, the current will come and touch this one in here, and then flows through the diode, come out from the other side, which is the same wire, by the way. And then I picked it up with this black wire to connect the current. Now is coming in here and through the resistor, coming from the other side, which is again this different location. And once I connect it at this point, basically the circuit is completed, and the entire circuit now is actually in series. So this is a series connection. There is another way of doing that. I could have done it. I could have put this point on the same voltage as this one, and this point on the same voltage with this one, and now all of a sudden it's actually parallel, no longer series. But then I would risk running tremendous voltage across the diode that probably will going to not work, because I think it's going to burn. Okay, so you don't want that. You're going to damage it. Okay, so you take, for example, from the source, let's say a battery. This is the positive of the battery. You go through component one, whatever, the resistor, for example, another resistor, a light bulb, whatever, something else, for example, your computer, and you come from the other side to the negative side of the battery. These are in series, one after the other. The current is the same. The charges that come through this device, they will emerge from the other side. The charges that come from this device, they will emerge from the other side. The charges that, all the charges that will come coming from the other side, and that is because charges are conserved. Okay? Because of the conservation of charge, the series is actually the same current. The parallel, on the other hand, it's not the same current, it's the same voltage. So I have to take, for example, my positive node in here, connect it to this device, and connect it to the negative side, and then take it from the positive side of the battery again and connect it to another device in here, okay? And then connect back to the negative side. So these two are the same height. And these two are in the same height. So there is the same difference of potential between the two devices, okay? So parallel is, on the other hand, same voltage. And that is your item 2 of the discussion today. Series connections, same current. Parallel is the same voltage. That is exactly what's going on in your house. Every plug in your house is the same. All of them 120 volts. So your house then is connected. There are two ends in here, okay? In parallel. Does this make sense? Does it make sense to you guys? Because the first one involves the conservation of charge. The charge that leaves one device, because it's in series with the other one, will hit the second device, and the second device will receive the same charge to transmit it to the third one, and the fourth one, and the fifth one, as many as you want. Okay. Same thing like I did in here, like that. This example is actually an example of a series. Okay. Same charge that leaves from my positive in here, from my battery, which is this entire side is positive, by the way, goes through the diode, then is connected through in series with this one, because it's going to hit the resistor. After the resistor is going to come out and come from back to the battery. So the resistor and the diode now actually in series, although it doesn't look like it, because this wire is the one that ensures that they are in series, because the charge that leaves the diode from this side is going to come and hit the resistor from the other side. So it's the same charge. So this connection is a series connection. A parallel connection, though, is where the voltage is the same. Okay. For example, in your household, all the plugs in your household, they have the same voltage, 120 volts. So they are in parallel, they are not in series. Does this make sense to you guys? Okay, so this is item 2 of the discussion today. Please try to remember that. That's very critical. Okay? If anything you take from this discussion, hopefully this point too. So again, this is an illustration of the series circuit. So the current leaves the positive. Yes, item 2, Jaren. So the current leaves the battery, goes through the first light bulb, then goes basically through this resistor and comes back from, because light bulbs are just resistors. And then it comes from the other side, goes through the second light bulb, comes from the other one, goes through the third light bulb, and comes through the other one. The current is the same throughout the entire circuit, okay? The voltages are not the same though, because this voltage drop is different. This voltage drop is not necessarily the same voltage drop in here. It depends on how much resistance in here and in here. So let's say, for example, this is 10 ohm and this is 20 ohm, okay? And the current, for example, for the sake of argument, is 2 amps. Then the voltage drop in here is 2 times 10 is 20 volts. Whereas the voltage drop in here is 40 volts, okay? Let's say, for example, for the sake of argument, this is 5 ohm. Then this is 5 times 2, this is 10 volt. So the entire voltage drop then is 20 plus 40 plus 10, which is 70 volts. This is your 70 volt battery that provided that thing, okay? So the voltages may or may not be the same. It depends on the resistance though, okay? So that is the series circuit. So again, the total voltage across the circuit divided among the voltages and the devices is the sum of the voltage drops. That's exactly what I was illustrating in here. The total voltage drop in here, which I calculated to be 70 based on my numbers, is 20 plus 40 plus 10, okay? The voltage drop across each device are proportional to its resistance. That's why I have 10 ohm, the voltage drop is 20 because the current in here is 2. The voltage drop is twice as much. I mean, the resistance is twice as much. The voltage drop is twice as much. The resistance is half as much. The voltage drop is half as much. So that is the second point of this discussion. If one device fails, current in the entire circuit ceases. If this one, for example, blow out, then there is no current flowing through it, which kills it everywhere. Okay? The current will stop everywhere. Okay? This, on the other hand, is a parallel circuit. Okay? If this battery, for example, to go back into the same example of 70 volt, the drop between A and B is 70, whether you go through this light bulb or this light bulb or this light bulb. Okay? Now, the fact that there is a broken circuit in here because the switch is open, there is no current at all. So it's zero current in here completely. Okay? But how much current? Let's say go back to our initial example in here. So this was, how much was the first resistor in our example? I put it to be 10, and the second is 20, and the third is 5. So this is a 10 ohm. The second one is 20 ohm. And the last one is 0 ohm. I mean 5 ohm. I'm sorry. Why am I 0 ohm? There is no such a thing. Okay. So, and it's 70 volt. The 70 volts is across this one. So there is a current of 70 divided by 10. So there is a 7 amp running through this one. Okay. It's going to run super bright. There is actually 70 divided by 20, and that is 3.5 amps through this one. Okay. So the current is not the same, but the voltage is. And the last one, there is no current because the switch is open. Even if this one blows, the current can still run through the other two. Okay. So these are some of the differences in here. The voltage is the same. If it's 120 volts, it's 120 volts. In this example, I took 70 volts, okay, for this battery. So it's providing me 70 volts. The current is the sum of the currents now. So how much we're actually taking from the battery? We're taking 7 plus 3.5 plus 0. So 7, add to it 3.5, add to it 0 amps. We're taking 10.5 amps from the battery, the sum of them, okay? So the currents may not be the same in the parallel, unlike these the series, which they have to be the same. The parallel, no, the voltages are the same. Okay. So again, these are the characteristics of this thing. As the number of parallel branches is increased, the overall resistance of the circuit is decreased. A break in one path does not interrupt the flow of charges in all of the other paths. When two identical lamps in a series are connected in a circuit are connected in parallel, the total resistance is actually less than that of either. Okay, actually it's going to be half. Okay. So the question here, consider a lamp powered by battery charges flow out of the battery and into the lamp. But if it's into the lamp, it ends there is no circuit. It has to be complete. It has to go, the charges have to complete through the entire circuit. So the charge actually goes through all of them. Okay. Let's see here. Does it make sense, B? From the negative terminal to the positive terminal. The charges actually flow from the positive to the negative always. Okay, I know you're talking about electrons, but that the electrons will move from the negative to the positive. But when we talk about current, the current is actually flowing from the positive to the negative. This is the negative, so it's flowing this way. Okay, so that is the current. Charges are moving from positive to negative. You and I know that they are electrons, and they're actually, to make the charges move from positive to negative, the electrons are actually moving this way. But ignore this thing in here. Always think about it from positive to negative, okay? Because they're minus times minus is positive. With a slight time delay after, no, that doesn't make sense. Switch, where is the switch? We don't even have a switch in the circuit, okay? Through both the battery and the lamp. That is exactly, the charges are coming from here. When they reach this point, they basically cancel the negative charges in here, and we have a problem. The battery will drag them and move them to the other side, okay, to complete the circuit. So that is the correct answer. So that is the whole picture, okay? So the correct answer is D. Okay. And this is basically what I was talking about in here for the parallel circuits. Okay, this is how homes are wired. Okay. And you have circuit breakers sometimes are needed to basically infuses to control the circuit. Okay. So these are some of the ideas related to currents. I know you have a couple of items today. The first one, does anybody remember it? The charger is responsible for? Yes, okay, very good. So as long as you guys are on board, so it's basically, hopefully you guys go through the those who are not watching live, so that you can get your answers to the discussion. The second one has to do with parallel and series circuits. Do you remember it, Taryn, now? Okay, very good. So I will be updating the grades hopefully sometime this weekend, okay? And you mean question number 2, you mean, Michelle, no? Question number 2? Okay, basically that there are two kinds of circuits, okay? That there is a parallel circuit and the series circuit. And in the series circuit, the currents are the same. In the parallel circuits, the voltages are the same. And that's mainly how households are connected. Does this make sense now? Okay, good. So I will see you guys on Thursday, okay? And hopefully you will enjoy the rest of the night. I'm going to go and watch actually the election results tonight. Hopefully to get also your video up and going for the other people. Let me stop recording because